Hello friends, welcome to my lecture on nonlinear partial differential equations of first order. Let us consider the problem of finding the solutions of the partial differential equation f x by z pq equal to 0, p is partial derivative of z with respect to x, q is partial derivative of z with respect to y, where the function f is not necessarily linear in p and q. We know that the partial differential equation of two parameter system f x by z a b equal to 0 is of this form. This we can easily prove. If you differentiate f x by z a b equal to 0 with respect to partially with respect to x, what we get is partial derivative of f with respect to x plus partial derivative of f with respect to z into partial derivative of z with respect to x. So, we have f x plus p f z equal to 0, and when we differentiate f x by z a b equal to 0 with respect to y, we get partial derivative of f with respect to y plus partial derivative of f with respect to z into partial derivative of z with respect to y, which is q. So, f by plus q f z equal to 0. Now, the two equations f x plus p f z equal to 0, f by plus q f z equal to 0 and the given relation f x by z equal to f x by z a b equal to 0 will lead us to a relation of the form 1, okay, when we eliminate the constants a and b. So, in generally it is possible to eliminate the arbitrary constants a and b from these three equations to arrive at a partial differential equation of first order, that is f x by z p q equal to 0. The converse of this result is also true, that is any PDE of the type 1, any PDE of the type 1 f x by z p q equal to 0 has a solution of this type f x by z a b equal to 0. Later on in this course you will be taught the methods by which we can find the solution of f x by z p q equal to 0 in the form 2, that is capital F x by z a b equal to 0. So, the converse also holds true. Let us now show that any envelope of the system 2 touches at each of its points a member of the system. What do we mean by an envelope? Let us see. The envelope of a family of surfaces is tangent to each surface in the family along the characteristic curve in that family. Now, let us make it more clear. Suppose we have a one parameter, let us begin with a one parameter system of surfaces. A one parameter system of surfaces is given by f x by z a equal to 0, where a is a parameter. Let us consider another member of this family by taking a as a plus delta a. Then f x by z a plus delta a equal to 0, the surfaces 3 and 4 will therefore intersect in a curve. This curve is also the intersection of the surface 3 with the surface whose equation is 1 by delta a f x by z a minus f x by z a plus delta a equal to 0. Why? Because when because the curve which intersects the which is obtained by the intersection of the surfaces 3 and 4, okay, will satisfy f x by z a equal to 0 will be this curve f x by z a equal to 0 and f x by z okay. So, the curve of intersection of the surfaces 3 and 4 will be given by these two equations, and when these two equations hold, this equation f x 1 by delta a f x by z a minus f x by z a plus delta a will also hold. Okay. So, the curve of intersection of the surfaces 3 and 4 will also be the curve of intersection of the surface 3 and the surface given by this equation. Now, as the parameter delta a tends to 0, this curve of intersection tends to a limiting position, which is given by the partial derivative of a f x by z a, here f x by z a equal to 0. So, when your delta a goes to 0, f x by z a minus f x by z a plus delta a divided by delta a will tend to the partial derivative of f x by z a with respect to a. Okay. So, the curve of intersection tends to a limiting position, which is given by this equation 3, that is f x by z a equal to 0, and the equation partial derivative of f x y z a with respect to a equal to 0. Now, this limiting curve is called the characteristic curve of the system on the surface 3 or the characteristic curve of 3. Geometrically, it is the curve on the surface of 3 which is approached by the intersection of 3 and 4 as delta A goes to 0. As the parameter A varies, the characteristic curve 5, this one given by these two equations traces out a surface whose equation g x by z equal to 0 is obtained by eliminating A between the equations 5. So, we eliminate the parameter A from the two equations f x by z a equal to 0 and partial derivative of f x by z a with respect to a equal to 0. This surface is known as the envelope of the one parameter system. For example, let us consider x square plus y square plus z minus a whole square equal to 1. The characteristic curve to the surface 6 is the circle x square plus y square plus z minus a whole square equal to 1, z equal to a. Let us see how we get this. So, let us find the partial derivative of this is let us write f x y z a, f x y z a is equal to x square plus y square plus z minus a whole square minus 1 equal to 0. Okay. And when we differentiate it with respect to a, what we get 2 times z minus a equal to 0 or into minus 1, 2 times z minus a into minus 1 equal to 0 or z minus a equal to 0. Okay. So, the curve of intersection of the surfaces f x y z a and the surface this when delta tends to 0 is given by f x y z a equal to 0 and the partial derivative of f x y z a with respect to a equal to 0. So, what we have z minus a. So, the curve of intersection, that is the characteristic curve, is x square plus y square plus z minus a whole square equal to 1 and z equal to a. Now, you can see x square plus y square plus z minus a whole square equal to 1, it is the family of spheres with radius 1 and centers on the z axis 0 0 a. So, it is a family of spheres with unit radius and having their centers on the z axis, and the characteristic curve of this surface is the circle given by x square plus y square plus z minus a whole square equal to 1, z equal to a. So, the circle lies in the plane z equal to a, and when we want to find the envelope of this family, then we eliminate the parameter a between the equations f x y z a equal to 0 and partial derivative of f with respect to a equal to 0. So, partial derivative of f with respect to a is z minus a equal to 0. So, z is equal to a. So, eliminating a between f x y z a equal to 0 and f x partial derivative of f x y z a with respect to a equal to 0, we get x square plus, because eliminating a from these two equations means you replace z by a here and that gives you x square plus y square equal to 1. So, we get x square plus y square equal to 1, which you know that represents a right circular cylinder. So, it is clear that now let us see this figure. This is your family of spheres x square plus y square plus z minus a whole square equal to 1 with center at the point 0 0 1 and having unit radius. Now, this is the characteristic curve x z equal to a x square plus y square plus z minus a whole square equal to 1. This is the characteristic curve which is a circle lying in the plane z equal to a having the center 0 0 a, and the envelope is this one, the right circular cylinder x square plus y square equal to 1. It is clear that the envelope x square plus y square equal to 1 touches each member of the family. Let us consider this member x square plus y square plus z minus a whole square equal to 1. Let us fix value of a, so that a member is fixed. So, this member is a member of the family of spheres with unit radius and having their centers on the z axis. So, this is one particular member. The envelope touches the member of this family along the characteristic curve, you can see here. Okay. So, the envelope touches each member of the family along the characteristic curve of the system on that member. Now, let us consider two parameter systems. Let us consider two parameter system of surfaces defined by the equation f x y z a b equal to 0. So, let us take a equation f where f is a function of x y z and a and b are two parameters. First, let us consider the case when b is a prescribed function of a. So, you are given b equal to phi a, where phi is a known function of a. Then the two parameter system reduces to a single one parameter system f x y z a phi a equal to 0. It is a one parameter family of surfaces. Its envelope is obtained by eliminating a. Now, it is a one parameter system of surfaces. So, its envelope is obtained by the equation f x y z a phi a equal to 0 and its partial derivative with respect to a equal to 0. Now, partial derivative of this with this f x y z a phi a equal to 0 with respect to a can also be written as partial derivative of f with respect to a plus partial derivative of f with respect to b, b is phi a into dB by dA equal to 0. So, this is another way, this equation is another way of writing the partial derivative of f x y z a phi a with respect to a equal to 0. Now, note that for every form of the function phi a, okay, let us note that whatever be the function phi a, the characteristic curve of the subsystem on 8, okay, the characteristic curve is obtained by this equation and this equation. Okay. The two equations together determine the characteristic curve. So, the characteristic curve of the subsystem, okay, on 8 passes through the point defined by the equations f equal to 0, f a equal to 0, f b equal to 0. Let us see that. Characteristic curve of this f x y z a phi a equal to 0, the subsystem f x y z a phi a equal to 0 is obtained from this equation and this equation. Now, it passes through the point which is determined by f a equal to 0, f equal to 0, f a equal to 0, f b equal to 0, because if f a equal to 0 and f b equal to 0, then obviously this partial derivative is equal to 0. Okay. The partial derivative if f a equal to 0 and f b equal to 0, then f a plus f b into dB by dA equal to 0. So, the point determined by f equal to 0, f a equal to 0 and f b equal to 0, okay, will always lie on the characteristic curve, okay, given by f x by z a phi a equal to 0 and this equation partial derivative of f with respect to a equal to 0. So, that is what we are saying, for every form of the function phi a, the characteristic curve of the subsystem passes through the point given by the equations f equal to 0, f a equal to 0, f b equal to 0. This point is called the characteristic point of the two parameter system on the particular surface 8. Okay. This is your two parameter system, okay, and we are taking the particular subsystem by taking b equal to phi a. So, this point is called the characteristic point of the two parameter system on the particular surface 8. As the point parameters a and b vary, this point generates a surface known as the envelope of the surface 8. The envelope is obtained by eliminating a and b from the equations f equal to 0, f a equal to 0, f b equal to 0. Now, let us consider for example, x minus a whole square plus y minus b whole square plus z square equal to 1. Then we can write this is a two parameter system of surfaces, you can see. So, here we consider f x y z a b equal to x minus a whole square plus y minus b whole square plus z square minus 1 equal to 0. Then we can see that partial derivative of f with respect to a is 2 times x minus a into minus 1 and partial derivative of f with respect to b is 2 times x minus b into minus 1. Hence, f x y z a b equal to 0 and f a equal to 0, f b equal to 0. Give us the characteristic point as you see f minus a is equal to 0. So, this is equal to 0, partial derivative of f with respect to b when we do find it should be y. Okay. So, minus 2 times by minus b. So, by minus b. Okay. So, x minus a equal to 0 means x equal to a, by equal to b. Okay. When we put this in this equation, we get z equal to plus minus 1. So, the characteristic points of the two parameter system on the surface 10, okay, on the surface 10 are a, b plus minus 1. Let us consider a subsystem of the equation subsystem 10. Let us consider a subsystem of this system by taking b equal to 2a. Then let us find the envelope of that surface. So, let us see, we have x minus a whole square plus y minus b whole square plus z square equal to 1, and we take b equal to a prescribed function of a, say b equal to 2a. So, what we do is since b is equal to 2a, we get x minus a whole square plus y minus 2a whole square plus z square equal to 1. This is one parameter subsystem. Now, in order to obtain its envelope, okay, let us put f x by z a phi a. Phi a is 2a here. Equal to x minus a whole square plus y minus 2a whole square plus z square minus 1 equal to 0. Okay. Now, let us differentiate it with respect to a. So, we get 2 times x minus a into minus 1, 2 times y minus 2a into minus 1 equal to 0. Or we can say we can divide this equation by minus 2. So, x minus a plus y minus 2a equal to 0. Here we will have minus 2, okay, because when we differentiate it with respect to a, we get 2 times x minus a into minus 1, then 2 times y minus 2a into minus 2. Okay. So, we will have x minus by x minus 2, we are dividing by minus 2 this equation. So, this will be 2 times. Okay. So, this gives you x plus 2y is equal to x plus 2y equal to 5a, or a equal to x plus 2y divided by 5. Okay. Now, eliminating a, the parameter a between this equation and this equation, okay, we will arrive at x minus x plus 2y divided by 5 whole square plus y minus 2x plus 4y divided by 5 whole square plus z square minus 1 equal to 0. And when we simplify, we will get 4x square plus y square plus 5z square minus 4xy equal to 5. Okay. We know that it represents a right circular cylinder whose axis is given by x over 1 equal to y over 2 equal to z over 2, and its radius is unity from our 3-dimensional geometry. Now, let us look at this. So, this is a surface, 2 parameter system of surface f x by z a b equal to 0. This is a 2 parameter system. Okay. F x y z a b equal to 0. We have this characteristic curve. Okay. On this, let us look at this. The envelope of a 2 parameter system is touched at each of its points p by the surface of which p is the characteristic point. So, this is the envelope. Okay. this is the envelope, it is touched at each of its points by the characteristic curve. Okay. You can this is the characteristic curve, and you can see the envelope is touched at each of its points by the surface of which P is the characteristic point. Therefore, it possesses the same set of values x, y, z, p, q as the particular surface, and therefore, it must also be a solution of the differential equation. So, we have three classes of integrals of partial differential equation of type 1. Type 1 means the equation of the form f x y z p q equal to 0 of this form. Okay. So, there are three types of integrals. Okay. So, there are three types of integrals of the partial differential equation of type 1. One is the two parameter systems of surfaces, okay, where the equation will be of the form some function of x by z and parameters a and b equal to 0. So, two parameter systems of surfaces to such an integral is called complete integral. Okay. So, that means systems parameters two parameter system surfaces will be given by f x by z a b equal to 0. Okay. This solution is called as a complete integral. Complete integral. If in the complete solution 2, okay, if in this complete solution b is replaced by a prescribed function, and we have if b is replaced by a prescribed function phi a and we obtain its envelope. Envelope is obtained by this equation and its derivative with respect to a equal to 0 by eliminating a between the two equations, and its envelope is obtained, we obtain a solution of the nonlinear PDE f x y z p q equal to 0. The totality of solutions obtained by varying this function phi is called the general solution of equation 1 corresponding to the complete integral 2 f x y z a b equal to 0. And the third is if the envelope of the two parameter system is obtained by, suppose your equation is f x by z a b equal to 0, then if you want to find the envelope, you eliminate a and b from these three equations f x y z a b equal to 0, f a equal to 0, f b equal to 0. If after eliminating a and b here, the solution that you get, it is called as the singular integral of the equation 1. Say for example, consider z square equal to z square into 1 plus p square plus q square equal to 1. Then x minus a whole square plus y minus b whole square plus z square equal to 1 is a solution of this equation with arbitrary a and b. So, here you can see in this relation there are two parameters a and b, and therefore, this solution will be a complete integral of the given PD z square into 1 plus p square plus q square equal to 1. Let us show that this is a solution of this equation. So, you have let me write f x by z a b equal to x minus a whole square plus y minus b whole square plus z square minus 1 equal to 0. Let us differentiate it with respect to x. Okay. So, then partial derivative of f with respect to x, when we find what we get 2 times x minus a, we get plus 2 z into partial derivative of z with respect to x. Okay. So, we get 2 times so we get x minus a equal to minus z into p. Similarly, when we differentiate this equation with respect to y, we get 2 times y minus b plus 2 times z into partial derivative of z with respect to y equal to 0, or 2 times y minus b plus 2 z q equal to 0, which will give you y minus b plus zq equal to 0. Okay. So, what we have z square p square equal to x minus a whole square z square q square equal to y minus b whole square, okay, and we have the equation x minus a whole square plus y minus b whole square plus z square e minus 1 equal to 0. Okay. So, replacing x minus a whole square by z square p square y minus b whole square by z square q square, we get this is a solution of this, means it must satisfy this equation. Okay. So, z square plus z square p square is x minus a whole square, z square q square is y minus b whole square, and we know that it is equal to 1. Okay. This is a solution of the equation 11. Since it contains two arbitrary constant, it is therefore the complete integral of the given PD. Now, let us put b equal to a here. Then we have one parameter subsystem x minus a whole square plus y minus a whole square plus z square equal to 1. Its envelope is given by x minus a by whole square plus 2 times z square equal to 2. So, this we can find, let us write it as f x by z a equal to phi a b, okay, a b, which is f x by z a phi a. This is equal to x minus a whole square plus y minus a whole square plus z square minus 1 equal to 0. Here phi a is equal to a. Now, we differentiate this with respect to a, we will get 2 times x minus a into minus 1, 2 times y minus a into minus 1 equal to 0. Okay. So, x minus a, okay, minus 2 we can divide, x minus a is, plus y minus a is equal to 0. So, x a is equal to x plus y by 2, a is equal to x plus y by 2. Let us replace the value of a in this equation. So, x minus x plus y by 2 whole square plus y minus x plus y by 2 whole square plus z square equal to 1. What does it give? 2x minus x minus y. So, x minus y whole square by 4 plus 2y minus x minus y. So, y minus x whole square. So, again I can write x minus y whole square by 4 plus z square equal to 1, and this is x minus y whole square by 2 plus z square. So, 2z square equal to 2. So, this is the envelope of the one parameter subsystem. Now, differentiating this equation x minus a whole square plus y minus a whole square plus z square equal to 1, what do you notice? You notice that this is 2 times x, differentiating this equation, differentiating the envelope. Okay. So, 2 times x minus by 4z into p equal to 0 if we differentiate with respect to x. So, 2zp equal to y minus x, and when we differentiate this with respect to y, what we get? 2 times x minus y into minus 1 plus 4zq equal to 0. So, what do we get? 2zp equal to y minus x and 2zq equal to x minus y. Okay. These two equations we get by differentiating the equation number 3 with 13 with respect to x and y, and then z square into 1 plus p square plus q square will be equal to z square plus zp is equal to y minus x by 2. So, z y minus x by 2 whole square, zq is equal to x minus y by 2. So, x minus y by 2 ka whole square, and what we get is z square plus x minus y whole square by 2, but x minus y whole square by 2 plus z square is equal to 1. Hence, the envelope which we obtained from the one parameter subsystem is an integral surface of the given PD. It is therefore a solution of type B. Okay. In type B we said what? Let us look at that again. If in the complete integral A2, okay, complete in the two parameter subsystem, B is replaced by a prescribed function of A, that is phi A, and its envelope is obtained, we obtain a solution of 1. So, envelope is equal to this one what we got, x minus y whole square plus 2z square equal to 1, and we have seen that it is a solution of this equation 1. The totality of solutions obtained by bearing phi a is called the general integral of 1 corresponding to the complete integral 2. Okay. Now, here we took a particular value of phi, that is phi a equal to a, and we found that envelope, but when v is equal to phi a and phi is arbitrary, the elimination of a between f x by z a phi a equal to 0 and partial derivative of f with respect to a is not equal to 0 is not possible. Okay. So, general integral can never be expressed as a single equation involving an arbitrary function. The envelope of two parameter subsystem 12 is given by, now let us look at this equation number 12. Equation number 12. Okay. So, x minus a whole square plus y minus b whole square plus z square equal to 1. When we find the envelope of the two parameter system, envelope of the two parameter system means we have x minus a whole square plus y minus b whole square plus z square equal to 1. So, I write z square minus 1 equal to 0. So, this is f x y z a b. Okay. So, this is the equation, and then f a equal to 2 times x minus a into minus 1 equal to 0, and f b is equal to 2 times y minus b into minus 1 equal to 0. Okay. Solving these three equations, what we get? Z square equal to 1. Okay. So, z is equal to plus minus 1. Eliminating a and b, okay, eliminating a and b from f equal to 0, f a equal to 0, f b equal to 0, we get z equal to plus minus 1. So, the characteristic points are a b plus minus 1, while the envelope is given by eliminating a and b from these three equations, f equal to 0, f a equal to 0, f b equal to 0, which gives us z equal to plus minus 1, and which represents a pair of parallel planes. Okay. So, the envelope of the two parameter system is given by z equal to plus minus 1. These planes are the integral surfaces of the given PDE, given PDE 11, this one. Okay. Because z equal to plus minus 1 means when we differentiate z with respect to x, p is equal to 0, when we differentiate z with respect to y, q is equal to 0. So, clearly z equal to plus minus 1 satisfies 11. So, these planes are the integral surfaces of the equation 11. Further, they constitute the singular solutions. Okay. As we described the third case, if the envelope of the two parameter system exists, it is also a solution of 1, it is called the singular integral. So, z equal to plus minus 1 are the singular solutions of the PDE, z square times 1 plus p square plus q square equal to 1. Now, it is possible to obtain different complete integrals which cannot be obtained from one another merely by a change in the choice of arbitrary constants. However, once one complete integral has been obtained, then every other solution, including every other complete integral, appears among the solutions of the type B and C corresponding to the complete integral found by us. Let us see how it happens. Y minus mx minus c whole square equal to 1 plus m square into 1 minus z square. It is a complete integral of equation 11. Equation 11 is z square times 1 plus p square plus q square equal to 1. Okay. Let us show that this equation 14, okay, gives us a solution of this equation. So, 2 times we differentiate with respect to x, 2 times y minus mx minus c into minus m is equal to 1 plus m square into minus 2z derivative, partial derivative of z with respect to x, that is minus 2zp. Similarly, we differentiate with respect to y, 2 times y minus mx minus c, when we differentiate with respect to y we get 1 is equal to 1 plus m square into minus 2zq. So, what we get here, we can cancel minus 2 on both sides. So, y minus mx minus c times m is equal to 1 plus m square into zp, okay, and y minus mx minus c, we can also cancel minus 2 here, is equal to 1 plus m square into zq. Now, what? So, y minus mx minus c into m is 1 plus m square into zp, and this is into zq. Now, we have z square plus z square p square plus z square q square. Let us put the value here. So, this is z square plus z p is what, by minus mx minus c whole square into m square upon 1 plus m square whole square plus z square q square is by minus mx minus c whole square over 1 plus m square whole square. Achha, z square q square. Now, this is what, z square plus we can take 1 plus m square whole square. So, what we get, by minus mx minus c whole square into 1 plus m square divided by 1 plus m square whole square. So, this 1 power will cancel with this here. Now, by minus mx minus c whole square upon 1 plus m square is 1 minus z square. So, this is z square here. So, z square plus 1 minus z square, and this gives you 1. So, this is a complete integral of equation 11, and you can see that we cannot obtain this complete integral from the complete integral 12 merely by a change of variables, this one complete integral 12, okay, x minus a whole square plus y minus b whole square plus z square equal to 1. Merely by changing the arbitrary constants a and b will never give us this solution, this one, by minus mx minus c whole square equal to 1 plus m square into 1 minus z square. But we find here that the 14th is the envelope of the 1 parameter subsystem of 12 if we take b equal to ma plus c. So, let us consider that the question 12, this is equation number 12. Okay. Here if you take particular value function b equal to phi a, then we will be able to get that solution. Let us see how we get that. So, we will take b equal to ma plus c. So, x minus a whole square plus y minus b, ma minus c whole square plus z square minus 1 equal to 0. This is f x y z a phi a. Okay. When we differentiate it with respect to a, we get 2 times x minus a into minus 1 plus 2 times y minus m a minus c into minus m equal to 0. Okay. Now, we can eliminate a between this equation and this equation, x minus a whole square plus y minus m a minus c whole square plus z square minus 1 whole z square minus 1 equal to 0. We will arrive at this solution, y minus mx minus c whole square equal to 1 plus m square into 1 minus z square. So, this complete integral can be found from that complete integral given by equation 12 if we take if we consider the 1 parameter subsystem of 12 with b equal to ma plus c. So, here what we will get, if you divide this equation by minus 2, you get x minus a plus m times y minus m a minus c equal to 0. So, we can find the value of a from here. Okay. A will be equal to how much, x plus m by minus m c divided by 1 plus m square. So, this value of a when you put in this equation, okay, in this equation we will arrive at the equation 14. Let us now consider another example. We have a first order nonlinear PDE z equal to px plus qy plus p plus q minus pq. First we show that z equal to ax plus by plus a plus b minus ab is its complete integral, is a complete integral of this nonlinear PDE. So, z is equal to px plus qy plus p plus q minus pq. This is the PDE given to us. Let us differentiate it. Okay, so we have, and z equal to ax plus by plus a plus b minus ab. Okay, let us show that it is a complete integral of this nonlinear PDE. So, let us differentiate this with respect to x, partial derivative let us find P, this is equal to A, and when we find Q, what we get is B. Okay. So, replacing A and B by P and Q, what we have, you see here, replacing P and Q by A and B, what we get, Z equal to AX plus BY plus A plus B minus AB. Okay. So, we can see that this is a complete integral of this partial differential equation. Now, let us show that the envelope of all planes corresponding to the complete integrals provides a singular solution of the equation. So, for that we have to find, let us write f(x) by z AB equal to z minus AX minus BY minus A minus B plus AB equal to 0, and find its partial derivatives with respect to A and B. So, let us find partial derivative of f with respect to A, what we get, minus x minus 1 and then we get here plus B. Okay. And similarly, partial derivative of f with respect to B, if you find, what you get, minus by minus 1 plus A. Okay. So, f then f A equal to 0 gives B equal to x plus 1, and f B equal to 0 gives you A equal to by plus 1. The complete the envelope of all planes corresponding to the complete integral, this is the plane corresponding to the complete integral, provides a singular solution. So, let us find the singular solution. The singular solution is obtained by eliminating A and B between these three equations. Okay. So, let us put A equal to by plus 1 here and B equal to x plus 1. So, then eliminating A and B. Okay. Let me call it 1, this is 2, this is 3. Okay. Between we get z equal to, we have Ax, z equal to Ax means by plus 1 into x, okay, and then B is equal to x plus 1. So, x plus 1 into y, okay, minus A minus B, so minus by plus 1 minus x plus 1, and then we get plus x plus 1 into by plus 1. So, let me simplify, z equal to x by plus x, okay, then we have x by plus y, okay, we have minus by minus 1 minus x minus 1, then let us multiply x plus 1 and by plus 1, we have x by plus x, okay, and by plus 1, x by plus x, then we multiply, we are multiplying x to by plus 1. So, x by plus x, then by multiply 1 to by plus 1, so we get by plus 1. Okay. So, what we get, this x we can cancel with this x, by we can cancel with this by, and we have the envelope as envelope, this is given by, you see, z equal to 1xy, this is 2, this is 3. So, we have 3xy, and then we have x plus y, 1 we can cancel with 1 here, Okay. So, we have 1, 2, 3 xy and then x plus y, and we have minus 1. Okay. So, this is the envelope of the all planes corresponding to the complete integral. This is the singular solution of the equation. Now, let us determine a general solution by finding the envelope of those planes that pass through the origin. So, if this plane z equal to ax plus by plus a plus b minus ab, okay, passes through the origin, then what we will have? 0 equal to 0 plus 0, a plus b minus ab equal to 0. Okay. So, then a plus b minus ab, this will be equal to 0, and what we will get? B times, if you take it to the other side, b times a minus 1 equal to a. So, we will get b equal to a upon a minus 1. Okay. So, thus in order to get the general solution, what we will do is, now let us consider the equation z equal to ax, b is a over a minus 1 into y. Okay. Z equal to ax plus by, a plus b minus ab is 0, which gave us the value of v equal to a over a minus 1. So, substituting b equal to a over a minus 1, we get z equal to ax plus a over a minus 1 y. Okay. Now, let us consider. So, now then thus z f x by z a phi a. Okay. Phi a is b equal to phi a, which is a over a minus 1. Okay. So, this is ax plus a over a minus 1 y minus z equal to 0. So, let us now determine partial derivative of f with respect to a, and we get x, and this I can write a over a minus 1 can be written as 1 plus 1 upon a minus 1. Okay. So, when we differentiate a over a minus 1 with respect to a, what I will get is minus 1 upon a minus 1 whole square into y equal to 0. So, let us put this equal to 0, then what we will get? X over y equal to 1 over a minus 1 whole square, or a minus 1 whole square equal to y over x. So, this gives you a equal to 1 plus minus square root y over x. Now, let us eliminate a parameter a between this equation and this. Okay. So, eliminating this, we call it as 4 and this as 5, this as 5. Okay. So, between 4 and 5 we get, okay. So, a is 1 plus minus ax plus, we have ax plus 1 plus 1 upon a minus 1. Okay. Into y equal to z. Okay. So, a is 1 plus minus square root y over x, this is a into x, and then we have 1 plus 1 upon a minus 1. 1 upon a minus 1 is plus minus square root x over y. So, plus minus square root x over y into y equal to z. This is what we get, and this is x plus minus under root x y, and what we get here plus y plus minus square root x y equal to z. So, I can also write this as x plus y minus z equal to minus plus 2 under root x y. Now, squaring this both sides, I get x plus y minus z whole square equal to 4xy. So, that is the general solution. Now, let us consider one more problem of first order nonlinear PDE x p q plus y q square equal to 1. By Charpit method, you can show that there are two complete integrals. One is z plus b whole square equal to 4 times a x plus y. The other one is k x into z plus h equal to k square by plus x square. What we have to do here, we want to show that the complete integral b can be obtained from the completed integral a by taking b equal to h plus a k. So, let us take b equal to h plus a k, then a becomes z plus h plus a k whole square equal to 4 times a x plus y. This is what we get, z plus h plus a k whole square equal to 4 times a x plus y. We can write f x y z a phi a, because we are writing b as this is phi a, b equal to h plus a k equal to phi a. So, f x y z a phi a will become z plus h plus a k whole square minus 4 times a x plus y equal to 0. And let us differentiate this partially with respect to a. So, partial derivative of f with respect to a is 2 times z plus h plus a k into k minus 4x, we put it equal to 0, okay, and determine the value of a. So, this gives you z plus h plus a k, z plus h plus a k into k equal to 2x, okay. So, what we get, this implies a is equal to 2x minus k times z plus h divided by k square, okay. Now, let us eliminate a between this equation and this equation, okay. So, let me call it as 1 and this as 2. So, eliminating a between 1 and 2, okay, 1 and 2. What we will get, z plus h plus a k, z plus h plus a k is 2x by k, okay. So, 2x by k whole square equal to we have 4 times a into x plus y. So, a is 2x minus k times z plus h divided by k square into x plus y, okay, or I can write it as 4x square upon k square equal to 4 times 2x square minus kx into z plus h plus k square y divided by k square, okay. So, this k square will cancel with k square, 4 will cancel with 4, and what we will get, we will have x square equal to 2x square minus kx into z plus h plus k square y. So, I can say that 0 equal to x square minus kx into z plus h plus k square y. or we can say that kx into z plus h equal to x square k square y plus x square, and which is the complete integral b. Okay. Given by b. Okay. So, with this I would like to end my lecture. Thank you very much for your attention.